Drop an egg into boiling water, and something irreversible happens. Not just cooking, not just hardening. At a molecular level, heat permanently changes the egg, and once that change happens, there is no way back. An egg looks simple, but inside it is a surprisingly complex system. It is mostly water, mixed with proteins, fats, vitamins, and minerals. What really matters when we cook eggs are the proteins, because proteins are the structures that respond most dramatically to heat. In a raw egg, these proteins are carefully folded. Each protein is a long chain of amino acids, twisted and coiled into a very specific shape. Those shapes are held together by weak chemical forces. As long as those forces stay intact, the egg remains liquid. That is why raw egg whites are clear and runny. The proteins are floating freely in water, slipping past one another without sticking. But the moment heat is applied, everything changes. Heat introduces energy into the system. That energy causes the proteins to vibrate. As vibration increases, the weak forces holding those folded shapes together begin to break. The proteins unfold. This process is called denaturation. Denaturation does not destroy protein, it changes its structure. Once unfolded, the proteins expose new surfaces, and those exposed surfaces start interacting with each other. They collide, they bond, they tangle together. As more and more proteins link up, they form a network. That network traps water in place. And that is the exact moment the egg stops flowing. What you experience as a solid egg is actually a microscopic web of tangled proteins holding water inside it. This also explains why egg whites turn from clear to white. It is not burning, it is not coloring. The tangled protein network scatters light differently, and your eyes interpret that as white. Temperature matters more than most people realize. Egg white proteins begin to denature at around 62 to 65 degrees Celsius. Egg yolks need slightly more heat, closer to 65 to 70 degrees. That difference explains something familiar. When you soft boil an egg, the white becomes firm while the yolk stays runny. You are watching two different protein systems respond to heat at different thresholds. But here is the critical part. Once these protein bonds form, they do not easily break apart. Lowering the temperature does not refold the proteins. Cooling an egg does not reverse cooking. That is why you cannot uncook an egg. The change is permanent. The same chemistry explains why overcooked eggs feel rubbery. At moderate heat, proteins unfold and link gently. The structure stays soft. But at higher temperatures, those proteins tighten. They squeeze water out of the network. That is when eggs become dry, springy, or chalky. The protein is still there. The structure has simply changed. This chemistry also affects digestion. Raw egg proteins are harder for your body to break down. Their tightly folded shapes block digestive enzymes. When eggs are cooked, those proteins are already unfolded. Enzymes can access them more easily. Digestion becomes more efficient. Amino acids are absorbed more effectively. This is why cooked eggs generally provide more usable protein than raw eggs. Heat does come with trade-offs. Some vitamins, especially certain B vitamins, are sensitive to prolonged high heat. Moderate cooking preserves most nutrients. Excessive heat over long periods can reduce some micronutrients. So cooking is always a balance. Enough heat to denature proteins, but not so much that structure and nutrients are lost. And this science does not stop with eggs. Meat, fish, dairy, and even plant foods all rely on controlled structural changes. Cooking is not just preparation, it is applied chemistry. So the next time you cook an egg, remember this. You are not just making breakfast. You are triggering molecular transformations that change structure, texture, digestion, and nutrition. That is what heat does to eggs.